This semester we've learned about differentiation. So as a motivating example, we talked about position being differentiated with respect to time to give us velocity, and then again differentiated with respect to time to give us acceleration. But unfortunately, the universe doesn't like to work that way. So Newton's second law, as an example, says F equals ma, and we're provided with the acceleration. So if we're given acceleration, how do we then go and find velocity and position? So the question really is, how am I going to go backward? And if you look at this little diagram, you could probably see that, hey, I took a derivative to go from position to velocity to acceleration, so I'm going to have to somehow undo the derivative. And that's really our question. How do we undo a derivative? And a simple way of thinking of it would be to say, okay, look, I know that velocity, when I differentiate it, this is going to give me the acceleration. And in a Newton's method example, that'll say something like, all right, you know the acceleration is 9.8 meters per second. How do I figure out velocity? How do I move this thing over to the other side? And that's what we're going to be studying here. Now we're going to give this a name. We're going to define what this thing is. We'll say a function, capital F, is called an antiderivative. We're going to call it an antiderivative of little f if we get this relationship. The derivative of the antiderivative is the function that we're looking for all the x on some interval. So that'll be our working definition. And you'll see that undoing a derivative is really kind of asking a question rather than something mechanical. Now, to try to illustrate this example to you, let's go back to what we were just talking about. Since the derivative of velocity is acceleration, this is going to say, according to the definition, that the derivative of this function is a. So we'll say that velocity is an antiderivative of acceleration. Similarly, right, if we say that the derivative of position is velocity, we'll say that position is an antiderivative of velocity. And to try to put this all together, we're going to come up with some nice notation that will really help connect things for us. And the definition of an antiderivative says this, okay, if you take the derivative of the antiderivative, you'll get the function you want. But our brains are really interested in having some sort of expression for this antiderivative by itself. So this is what I like to call the switcheroo. I don't want this derivative here. So what I'm going to do is move it over. I'm going to switch it all the way to the other side. I'm going to put it somehow connected to the little f to try to get this big F by itself. So the notation for derivative is this d by dx, but when we try to undo a derivative, we're going to use this notation, a big, long, stretchy s, and we're going to say that that is beside there. And this notation is kind of similar to what we're used to. This is the derivative, and this stretchy s with the dx connected to it, this is the antiderivative. And what's important is that the dx matches the variable in there in the same way that the x match the variable in there. So that's what we're going to be talking about, derivatives and antiderivatives. That's it. Those are the two notations that we want. Those are the two symbols that we want. And these are the questions that we're going to want. Now, to find an antiderivative is just we ask a question. And it all comes back to this definition here. What function do I differentiate to get this thing little x? That's all it is. The beginning, the basis of antiderivatives is just asking this question and then trying to answer it. If somebody writes down this expression, now this is basically asking for an antiderivative. Again, we're having these two letters match. And the question is, what do I differentiate to get the function on the inside here? And if you understand an antiderivative in that way, you'll find that finding a basic antiderivative is very easy. So if this is the question, then the answer we already know. Oh, since the derivative of sine is equal to cosine, we're going to switcheroo this. Then sine is the antiderivative of cosine. And that's it. That's the basic antiderivative idea. But there's one major difference here. Antiderivatives are not unique. I could have also said this. Hey, look, since the derivative of sine of x plus 2 is cosine of x, then when I switcheroo it, sine of x plus 2 is the antiderivative of cosine of x. This is legitimate. There's no difference in me saying this. There's no problem with me saying this. And in fact, any derivative of sine of x plus c, where c is just some arbitrary constant, would equal cosine, so that when I switcheroo, sine of x plus c will be the antiderivative of cosine. So you get infinitely many antiderivatives. And that's just a byproduct of the nature of the question here. So we're going to refine this symbol. When we say this thing, we put this stretchy s here, we are going to say that this is an indefinite integral. I prefer to call it antiderivative because I think it'll help keep things straight for you. But it's called indefinite because there are infinitely many antiderivatives that pop out. That's what that plus c is. So whenever we are working with antiderivatives this way, we've always got to remember the plus c, because the answer to the question is there are infinitely many different antiderivatives, and you have to be clear. Now, once you go ahead and you understand how the game works, you can see that coming up with antiderivatives is really easy. What do I differentiate to get e to the x? That's the question, and it's very easy to answer it. Well, since the derivative of e to the x plus any constant is itself, when I switcheroo this, I will get the answer. The antiderivative of e to the x, there isn't just one, there are infinitely many of them. It's e to the x plus c. That's what that indefinite nature means. Now, there are a lot of historic reasons for some of the silly notation you're going to see. For example, you will often see things written in this shorthand or sloppy notation. This is a bit puzzling because you might say, well, what is the function? Why is this dx thing on top of the x? The dx is nothing more than an indicator for what the variable is. Unfortunately, this sloppy notation has kind of persisted, and this is really what the question is. And if you think about an antiderivative as a question, what do I differentiate to get 1 over x? And we already know this. Since the derivative of natural log of x plus a constant is 1 over x, when I switcheroo, I will find that natural log of x plus c is what the antiderivative of this thing is. Now, similarly, this bad notation comes up in lots of other places. Now, there's a nice idea that allows us to tackle some applied problems. So if I say like this, if the velocity of a function is secant squared of t, and if we know that the velocity at time 0, or sorry, the position initially is 7, let's find the position at any time t. This is something called an initial value problem. You encounter these in physics all the time. You're given something about the velocity and you're told some initial state of the problem. Well, since the derivative of velocity is equal to position, that means when we switcheroo this, the position, the antiderivative of position is going to be the following, right? It's going to be given there. I think I've written this down wrong. Sorry, yeah. Sorry, I got this backwards. No wonder it wasn't working out. Since the derivative of position is velocity, that means if I ever want the velocity, I need to find the antiderivative of, if I want the position, I need the antiderivative of velocity. Whew, sorry about that. So that's going to tell me, okay, find the antiderivative of secant squared, and we are doing an antiderivative with respect to time. Okay, well, here's how we tackle this. Since the derivative of tangent plus any constant is equal to secant squared, this is just a basic antiderivative. We pull a switcheroo and we say that the antiderivative of secant squared of t with respect to t, remember these have to match, that is going to be tangent of t. So the position at any time is tangent of t plus a constant. Now I need to evaluate this constant with the initial conditions. And so we are told that s of 0 is 7. So if I take this position function and plug in 0, I'll get tangent of 0 plus c, and that has to equal 7. I know that the tangent of 0 is 0, so this tells me that c is 7. And that means I have determined the position function. I no longer have infinitely many antiderivatives. I have one antiderivative. It's the one antiderivative that satisfies the differential equation, and it satisfies the initial condition. And that's the important part here. One important question that we're going to encounter a lot here that we need to deal with is powers. And this is now a mechanical thing. So we're going to build up to this result. So when we build up to the power rule, we're going to get something, we're going to think about it in layers. Now, I already know the basic power rule. If I take the derivative of just some power of x, I bring the power down, and I get an x to the n minus 1. So if I were to switcheroo this, it would tell me that the antiderivative of n x to the n minus 1 is that result. And that's not quite what I want, right? The power is too low, and I don't want this thing in the front. So I'm going to have to reverse this to try to end up with the result that I want. So for example, I am now going to say, well, if I ended up with a power of n that was 1 too low, I'm going to increase the one that I start with. So I'll say x to the n plus 1 plus a constant. If I differentiate this, I'll get an n plus 1 x to the n. So when I switcheroo, I'll get x to the n plus 1 plus a constant is the antiderivative of this thing. Now that's better because I have the right power, but now I have this thing in the front. So finally, you can see what you should probably do to fix this. If I put a 1 over an n plus 1 downstairs, and this power upstairs, and I say, what is the derivative here? I'll get an n plus 1 that comes down from the power rule, and now it's going to divide with that, and I'll just get an x to the n. And that's perfect. So when I switcheroo, I'll get 1 over n plus 1, x to the n plus 1 plus a constant is the thing that I'm looking for. And so this is exactly the result that I want. This is the antiderivative power rule. The antiderivative of a power, all I do is change a power rule in reverse. I take the power, I increase it by 1, and rather than multiplying by an n, I divide by an n plus 1, and I add the constant. Now note, this doesn't work if n plus 1 equals 0. Now, if that's the case, we're going to get to the logarithm that we talked about, right? So if this was x to the minus 1, that would be the same as 1 over x dx, and we already talked about this from earlier. Now, I've already given a little clue here, right? So if I wanted to anti-differentiate this stuff, it's very easy. Using the power rule is simple, right? X to the 7 dx. I take the power, raise it by 1, put that number downstairs, add my constant, x to the 8 over 8 plus c. It doesn't matter how weird this thing looks. So if I go x to the 31 dx, and it's downstairs, I know that I can raise this, and just remember to add x to the minus 31 plus 1 over negative 31 plus 1 into a constant, x to the minus 30 over negative 30 plus c. And sometimes you'll get strange looking things, right? So you might get weird things that look like this, just a dx. And you say, well, what's the function? Well, this is again a leftover sloppy notation. The function is really a 1, and 1 you could interpret as x to the 0. So that would be x to the 0 plus 1 over 0 plus 1, and a constant, which is just x. Or another way of saying, what function do I differentiate to get 1? And the answer would have been x.